Today we're going to perform a lab, the purpose of which is to find the coefficient of static friction between two materials. Now, I don't care what two materials you use. Bottom line is you have to specify in your problem, in the form of a question, what two materials they are. So, for instance, if you used a wooden block, which I say I don't care which two materials you use, I do care what one of them is. You're going to use a wooden block as one of your surfaces. Your problem might be, what is the coefficient of static friction between a wooden block and the floor? What is the coefficient of static friction between a wooden block and the tabletop? What is the coefficient of static friction between a wooden block and the desktop? Whatever other material you use, make sure you specify what it is, because we want that problem to be specific. Your materials, they're up on the board right now. You're going to use a triple beam balance scale once to find the mass of this block of wood with some masses in it already. We'll call it a mass set. You want to find the mass of that once. Now, you're going to have to end up changing your mass throughout this experiment, but you don't have to keep remeasuring the mass because the mass on the masses themselves are printed. So that means that if you take off a 100-gram mass, just take off 100 grams off of what you weighed the mass set to be. If you add 200 grams to it, then just add 200 grams to whatever you measured the mass set to be. So measure the mass once, and then record the mass for every trial, but you don't have to keep remeasuring it as long as you're okay with subtracting it. Now, attached to that mass set is a string, and attached to that string is going to be our next piece of apparatus, which is going to be a force sensor. You're going to use a similar apparatus to what you've used in the past for your labs, except that this time it's not going to be a motion sensor, it's going to be a force sensor. So you're not going to hear that clicking sound when you press start on your iPhone. You're not going to hear anything. But rather, you're going to, as opposed to having the cart go away from or toward the motion sensor, you're going to physically pull the force sensor, which is connected by that string to the mass set, and then that's going to measure the force for you, the force that you were pulling with for you. Now, that force sensor is going to be connected to your AirLink apparatus. And remember that this is an older version of the AirLink. Okay, it's essentially the same thing. Okay, but this is just looks a little bit different than the one that you see up on the board right now. That AirLink will be connected to your iPhone. And your iPhone is going to be what ultimately collects the data. Now, good news for this one. When you collect the data on your iPhone, you're not going to have to export it, email it, export it, and import it into a spreadsheet. There's just going to be some numbers that you're going to read right off of the graphs on your iPhone and then write down on a piece of paper and then type them into a spreadsheet. So it should be a little less time consuming that way and a little bit easier that way, a little bit less confusing. What are we going to change through this experiment here? I'll give you the brief essence of what we're going to do, and then I want you to tell me what my manipulated variable would be. In essence, we're going to take that block of wood with the masses in it, we're going to pull it, and we're going to see what the maximum force is that's required to get it moving. So what force was required to get that block of wood moving? Then we're going to repeat that by changing the mass of that block of wood. Then we're going to see what force is required to get that one moving. Then we're going to change the mass again, see what force is required to get that one moving, and so on and so on and so on. What would be my manipulated variable there? The weight of the block, the mass of the block, a better way to say it would be the normal force, because that's what we're really concerned with, right? Now, we're changing the mass, but changing the mass is only a mechanism to change the normal force. So really what we want to manipulate here is the normal force. What responds to that? What changed because of the normal force? When I added mass to it and therefore changed the normal force, what changed because of that? Yeah, the force required for movement. So we could say that would be, well, we're going to measure that as our applied force, but that would correspond to, as we've learned over the last couple of days, my maximum force of static friction. The force that's required to get it moving, the maximum force of static friction. Now, control variables, I'm not going to give you any of those. You guys can come up with some of those on your own. There's a couple of them that you need to include. Okay, they're critical to this. If you change this or you change that, then all bets are off. The experiment is completely useless. There's other things that are kind of important as well, but there's a couple of them that are extremely important. You can't miss those. Okay? I don't expect you to have 15 control variables here. You need to have the one or two that are critical, and then hopefully have one or two more decent control variables. Beyond that, that's okay. Usually you take care of the really important things within 2 or 3 different control variables. The procedure you have written down in front of you, we'll talk about it in a little bit more detail here right now. It's the exact same thing as you see up on the board. So you're going to set up the apparatus as you saw in this diagram in the materials here. Okay, your force sensor is connected to the string, which is connected to the mass set, and then of course your force sensor is connected to the air link. Now ultimately what we're going to do is pull the force sensor with our 2 fingers. You'll see the 2 finger holes in the force sensor when you get one. Pull it lightly, 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 lightly. Pull it a little bit harder, pull it a little bit harder until the mass set begins to move. You should see on your iPhone instantly a graph being plotted of force versus time. What you need to do is look at that graph and measure off the maximum force that you applied. Okay. Now, that might be a little bit difficult on the scale of the graph that's given. You may have to change the scale by magnifying it or by making it smaller. You'll figure that out. Okay, that's kind of a on-the-fly thing that you're just going to figure it out as you go. A couple things you got to watch out for there as you're doing this. Number one, when you look at your iPhone after you've got this connected via Bluetooth, in the same way that you connected it over the last couple of labs, make sure that you're selecting the force pull positive option. There is a force pull negative option. You need to select the force pull positive direction. Basically what that's going to do is say, look, when I pull it, it's going to record a positive value of force as opposed to a negative value of force. So force pull positive. And you also want to make sure that before you actually go to do this, you zero the force sensor. There's a little 0 button right here. You'll see it when you get the force sensor. Make sure you press 0 before you start the experiment. It's not a bad idea to press 0 in between every trial, but it's critical that you press 0 at the beginning of the experiment, just in case it wasn't 0 before that. So you got this all set up. You measure the mass of the wooden block, including the masses on the wooden block. And then you're going to hook the force sensor on. You're going to pull it. You're going to begin pulling it after you press start on the app, on the SparkView app. You're going to pull it parallel to the ground. This is pretty important, pulling it parallel to the ground. If I pull it up at an angle like this, here's the wooden block, and I'm pulling the force sensor up at an angle like this, then that changes the normal force. The normal force is no longer the same as the force of gravity. If we pull it horizontally, like this, then the normal force is the same as the force of gravity, and it becomes an easier calculation for us to do. So pull it horizontally, parallel to the ground, until the wooden block begins to move, and then you can press you can press stop. Not on the force sensor, that should say press stop on the what? You press start on the app, you're going to press stop on the app as well. You're going to see a graph on your iPhone screen. It's going to be the applied force versus time. And the graph should look something like this. It probably won't look exactly like that. And you don't need to lose any sleep if it doesn't look exactly like that. The bottom line is you need to have a clear, distinct peak. That peak is the maximum applied force. The maximum applied force. That's what you need to record in your data table. The maximum applied force. Make sense? Well, then you're going to repeat these steps. Use a new mass for your wooden block. Pull it again. Measure the force that's required to get this wooden block moving with this new mass or this new normal force. Record that data. Do it again. Do it again. Do it again. And then when you're finished, you got a data table that's going to look something like this. Mass in kilograms, maximum static force friction. Then you're going to fill in an analysis table. The mass in kilograms is just copied over from your data table. So is the maximum static friction force. The normal force, you're going to have to calculate. You can do that by hand, or you can, as you plug numbers into a spreadsheet, have the spreadsheet do it for you. How are you going to do it? Whether it's by spreadsheet or by hand, how are you going to find the normal force? What's the normal force the same as if we're pulling this thing horizontally, parallel to the floor? The upward normal force on the block is the same as the downward force of gravity. So we're just going to say the normal force is m times g, mass in kilograms times 9.81. Then, finally, you're going to plot a graph. And your graph is going to be FSF max, the maximum force of static friction, versus the normal force. When you do that, you should get pretty much a straight line. Plot that graph on Google Sheets. Have Google Sheets include a linear line of best fit, and have Google Sheets include the equation, display the equation over here. Maybe my equation is 0.72x plus 0.0034. The coefficient of static friction here is the slope of this graph, 0.72, or whatever it works out to be. Once you've got that value of the slope, and therefore the value of the of the coefficient of static friction, I want you to write a conclusion, which should be two sentences. Sentence number one, the coefficient of static friction is 0.72, or whatever it is that you found. Sentence number two, this is known because, fill in the blank. So basically, what did you find? How do you know? Okay, I found the coefficient of friction to be 0.72. I know it because, however it is that you determined it was 0.72. And then finally, sources of error. You need 2 or 3 good sources of error. What could have went wrong? What could have been better? Could be your materials, could be your procedure, it could be all kinds of things. Anything that could have went wrong other than that old standby human error, which I can't stand. Okay? Don't make mistakes. No such thing as human error. Don't make mistakes. Okay? 2 or 3 good sources of error, and then the corresponding suggestions for improvement.